So as we get started this afternoon, my name is Eric Dyer. I am the Farm Robotics Academy coordinator, and I have with us esteemed panel of people who are our vendors for the virtual vendor fair for the Farm Robotics Academy. I'm also proud to have my partner in crime, Mr. Kelly Scott, who is Farm Robotics Challenge Director. The whole package is what we've got going now is a Division 1, 2, and 3 program. Division 1 are the universities, the four-year institutions. The Division 2 are the community colleges and tech schools, and the academy are for the high school divisions. Our program is growing quite well. We are international now with our competitions. And while this is the first year out with the Farm Robotics Academy, we are focused on California schools. We have teams from Washington, and we heard just recently, we have a team probably from New Jersey, and the National FFA just put out a splash for us, and we might get more participants beyond the borders of California. So personally, I'm a 39-year veteran of teaching agriculture, engineering, and horticulture and other sciences at Woodland High School. And that's how I got my start in this business. And now I'm in charge of putting together this fantastic program. So today we're going to have our vendors participate with us. And I'm going to give them 5 minutes to present to each one of them, to their description, and then we will go to a set of breakout rooms where you'll be able to ask more detailed questions. At 5:20 at the latest, we'll give a 5-minute warning, and then at 5:25 we'll all come back together for final summary. If anybody needs to go along the way, you're privileged to go. We will have a total of 7 vendors with us today. And let's have Chris, I'm going to let you start us out for this event for today.
All right, thank you, Eric. It was a great introduction. I'm very grateful for you to include us, and I like all of the growth in the agricultural industry and education that you're doing. So Pasco, a little bit of history about us is that we're about a 60-year-old company. We got started with physics, sensors, and experiments for higher education. And in the last 60 years, we've turned into a sensor company that has for physics, biology, chemistry, and in regards to this meeting, agriculture, environmental science, all wireless sensors, Bluetooth, with accompanying software and with a great user interface and ability to use. So I'm going to start off just really quickly out on our website.
Share your screen first.
I'm going to share my screen. Just give me one moment here. All right, so here is our website that shows all of our agricultural science sensors that you can purchase, and we can go over those in the breakout room if you like. And so here is our presentation for the day.
I'm not seeing your slide deck here.
Got it. Okay.
There you go.
How are you looking? All right, so we'll get started with our presentation.
There it is.
Okay, Chris Steele, Pasco. This is our farm research and automation. So our concept is that farming relies heavily on mechanized support. It's going to be data analytics, robotics, and sensors that kind of drive the way we understand farming and the way we can integrate with farming and innovate it as well. So we designed ways to measure live processes. So this is going to be with our real-time data. Our sensors can be used wirelessly, Bluetooth, either in a classroom with using your computer, or it can be used in the field and dedicate it'll actually keep the data in the sensor until you bring it to your computer, or you can actually use your cell phone to do it mobily as well. So we have sensors here. This is the soil moisture sensor. We have a turbidity sensor. Over here, we have containers basically creating mini greenhouses, CO2 sensors, and the sensor is ODO sensors. Okay, these are just a few of the sensors you can find in our agricultural kits, and we have many more as well. Okay, so we have a greenhouse sense and control kit. So this is our mini greenhouse. We have our greenhouse sensor that monitors things like soil moisture, humidity, light, and temperature. We have a fan here that controls the temperature and the humidity. We have lights up here that have red and blue lights. And we also have abilities to code using Blockly code in order to identify and then make changes to your system. Okay, so fully programmable greenhouses let students create and study their own environmental systems using Blockly programs controlling fans, water pumps, can measure light, temperature, soil moisture, humidity, and this all runs on our control.node and programs that can basically whatever your imagination can come up with. Okay, we also have wireless weather sensors. And this will control all of these um, qualities here. It can be controlled from your cell phone. You can have sensors coming there directly, and you can use our SparkView software to actually have GPS coordinates of each one of your sensors and the data that it's collecting. You can do that by going into software and going into the map tab, and this will show you one version of the map. You can collect data based on those points. More map options, so there's not just that one map, you can do other maps as well. Okay, here's another version of a map that you can use as a setting. And then the last one we have here is spatial analysis. And this is going to give you an overview so you can kind of see from a different perspective. This could be definitely used for farming purposes. Okay, that's all we have for the presentation in terms of the PowerPoint. I'd also like to go over an experiment if we have time. So we're going to go over the actual photosynthesis lab here in a quick detail. I'm going to introduce you to our friend Brandon.
Hello, everybody. My name is Brandon. I'm the sales engineer at Pasco. I just want to give you a quick demonstration of our greenhouse sensor control kit. So to do that, I'm going to open up our SparkView software, and I'll share the screen in a moment so you can see what I'm doing here.
So, Brandon, we're going
Yes.
to call time on you in about 2 minutes.
Okay, beautiful. That's all I need.
Okay.
Let's see here. I'm going to share my screen and so you can see SparkView. There it is. Okay. All right, and can you see everything there? So you should see 4-digit displays, each with a different data parameter, CO2, concentration, and then brightness, humidity, and temperature. So you should see up there, but let's
Yes, we
see.
can see it.
Okay, let me get that out of my way. Great, they're all there. Okay, so our entire greenhouse system is run off of the Pasco control node, which is the brain that controls everything. And so we do this with our Blockly coding by opening up the Blockly code tab up over here. Gosh, I need to hide this thumbnail. It's in my way. Anyways, so I'm just going to create a simple program just to turn everything on. So we have a fan, a light, and a water pump. So the first thing we want to do is just turn the light on. So we go into our hardware blocks here. Oh, yeah. Anyway, there we go. I'm going to set the grow light to a specified brightness that we choose. It mixes red and blue light to cover the full spectrum that simulates sunlight and thus inducing photosynthesis in our plants. Next, we kind of want this to just keep running forever. Mind you, as you're going through this, the students are thinking about the process that goes into designing plant care or crop care programs. So I'm going to make this permanently true by saying that to do this, loop while it's true. Well, it's always true, so it's going to be creating an infinite loop. And then I want it to turn on the fan. So we have a power output board that is connected. I would show you if I stop sharing the screen, but controls the fan and the water pump as told by the control node. So we'll have that turn on the fan, and then we'll just have it do nothing for 3 seconds, let's say. Because you want to put pauses in between these things, otherwise it tries to run too fast than it actually can, and then your programs crash. And that's just any general coding project. So sleeps are important. And then, there we go. Let me get this guy in here, and then change this to channel 2. So that way it'll turn on the fan, and then we'll sleep once again for 3,000 milliseconds. All right. And then,
Done with that.
yeah, so this will just turn everything on. And I'm going to hit start here. There we go. And so I'm going to stop sharing just so you can see the screen in full, exactly what's going on behind the code physically here. But you can't see in great detail. I've turned the light on now. That wasn't previously on. And I don't know if you can see it in detail, but you can see little water bubbles moving through this pipe if you have the camera large enough. And you can't hear it, but the fan is going now. So that's just the basics. You can do a function-based program like I did, or you can do sensor-based programs utilizing the sensors to, like Chris said, make changes to the environment.
Excellent. Hey, thank you guys for that quick presentation. I know it was brief. We'll give you more time here in a few minutes with the breakout rooms.
Great. Thank you so much.
Thank you very much, Chris. Okay, Mr. Arav from Bonsai Robotics.
Hi, everyone. I'm representing Bonsai Robotics here. A little bit of background of Bonsai Robotics. Bonsai Robotics recently acquired FarmNG that was making the Amiga platform. And FarmNG's mission was to help the smaller farmer have more accessibility to technology that the larger players are using. So the biggest thing that farmers are needing on their farm is the autonomy, and so that's what FarmNG was tackling with their Amiga platform. So we were building, I'm going to go ahead and share my screen here, but we were building this Amiga platform, and the platform we were going ahead and automating. So currently, Bonsai Robotics does very similarly the same things. We're sort of retrofitting larger equipment to run autonomously. We're currently doing these operations in orchard environments using larger tractors. So you can see here sort of two of our form factors running autonomously.
Today I'm out here.
You have the larger drones or the larger robots, as well as the tractors here on the left side. And you can see this is a spray tank that we run in the Central Valley. And then this is one of our Amiga platforms that's running in a pumpkin environment to be used as a harvest table. So we also have quite a big breadth in the high school and academic space. We teamed up with UCANR for the last 3 years to host something called the Farm Robotics Challenge. And the basis of that challenge is students from across the world take this Amiga platform and build custom software or hardware or a combination of both to solve a real-world application. And so we're excited to now spin that off more onto the high school space to have students take this same robot that universities and researchers and people in the industry are using and receive it fully unassembled. So students receive it in a bunch of parts. They go ahead and build the hardware first. They then go and wire the whole robot together electrically, and then lastly test the robot with some Python code. A little bit of background about the Amiga platform. It's a fully electric, modular, intelligent robot. It's modular in the sense that you can change the track width from 40 to 84 inches. So you can see here, these are, more configured to around the 40 inches, but we can go to something all the way up to 80 inches, which as you can see here, use with our fertilizer spreader. You can also change the wheelbase. So you can see here, this robot has a little bit of a wider wheelbase, and you are able to change the height of the robot as well. So everything's on a clamp-based system, allowing you to change the X, Y, and Z axis depending on the application at hand. And so this is nice that if you're not looking for your students to really work on the autonomy side, that they're able to really work more on the mechanical side to configure the Amiga, configure the robot to solve that real world application that a local farmer or maybe the farm on campus is having. The platform, like I just showed earlier, is intelligent. We, merge it with something called our intelligence kit, which you can kind of see here in this picture. This is a little bit of a better picture, but this intelligent kit is actually a compute module with a couple of very powerful cameras and a GPS antenna to be able to allow the robot to move autonomously. And so we have an open source environment which allows these students to take their own Python programming code and deploy it to the robot to do simple movement commands or to have it run an autonomous path or to do some detection. And so this is really nice because students get to, start from the ground up to build the whole robot. They understand about the hardware pieces, about the electrical pieces, and then they touch up on a little bit of the software. So they get exposed to all parts of engineering. And so what we're offering the robot, you're able to configure it based on how, you see your students best using it, either more in an autonomous sort of intelligent platform or more of a base bones platform with the 3-point hitch. So you can see the two platforms here. This is our what we call our research package, which students would be able to build and then start running autonomous paths with to maybe do some transporting, hauling, or data collection. And then you have our system with the 3-point lift kit, which is more for, students and teachers looking to actually run implements, tools, and, sort of do consistent applications. Maybe that's weeding, maybe that's cultivation, maybe that's mowing, but with their Amiga. And so I'll be sharing our website here. We actually already have several high schools who are involved in this program. One of them is Santa Cruz County Office of Education. This is our second year running the high school curriculum with them. They do a sort of a robotics after school program, but this year they're actually going to be doing it during during the school year, more in the spring semester. And I think the biggest, pretty cool thing about this is that, I'll be sharing a map here, which are all the universities that are currently using the Amiga for either research or the Farm Robotics Challenge. So for a lot of these students, they get to, when they're, applying for college or when they're looking for jobs, they're able to leverage that experience that they've had with the Amiga. And so we've already been seeing that firsthand with schools, specifically with Greenfield High School out here in the Salinas Valley, where several of their students were able to leverage it and get into some of the schools that they wanted, as well as in internship programs that are, very hard to get into. Um, and so, yeah, we also are sort of supporters in the Farm Robotics Challenge, and we have an Amiga Innovation Award that pertains to projects that would be using the Amiga specifically in the challenge. So for the Academy, we're offering a $1,000 specific reward just for, that sort of audience. But we also have a D1 and D2 division where, we have the upper education students as well as students more in the community college space. So if you have any questions, I'll be here during the little breakout room and would love to show you guys an in-person demo. I'm here in our office today, so I didn't want to bore you too much with all the technical stuff, but once we get into that breakout room, we can always sort of go into a live demo and I can really show you guys how you can program the robot or how you can control it.
Sounds good. Thank you, Rob. Good job. All right, Mr. Greg from Advanced Technology Consultants.
Hi, everybody. As Eric said, my name is Greg, and I work for a company called Advanced Technologies Consultants. I'm going to share a small catalog in the chat if you guys want to check that out. And then I've prepared a presentation here. So a little bit about us. We've been in business since 1964 and cover all manner of technical training equipment, curriculum, and certifications. That's a collaborative robot that we're working with. There's some mechanical drives trainers. A lot of this stuff applies directly to agriculture and agricultural technology. I don't know how many of you have been to Hartnell College in Salinas, but Richard Chapman started a agricultural mechatronics program with a partnership with us and Festo Didactic, our largest manufacturing partner. We're in over 2,200 schools at this point. And again, robot welders, HVAC, welding, we really run the gamut. Speaking of certifications, we have partnered with NC3, which is the National Coalition of Certification Centers. And they've been around for a little over a decade now, 15 years. And in October, they're going to hand out their millionth certificate. So just Festo certificates, we've handed out close to 25,000. This data is a little bit old. So this is industry recognized certificates that partner with manufacturers, Festo for manufacturing and agricultural technology, Kubota for diesel, Lincoln for welding, so on and so forth. So at Hartnell, Richard is starting his agricultural mechatronics program with this AC/DC trainer that has about 50 hours of curriculum that comes with it. Obviously, electricity is foundational and fundamental to any sort of robotics, any sort of technological pursuit. In addition to NC3 certifications with this, this and our Mech Lab, which I'll get to next, are the two components used in Skills USA's mechatronics competition. So if you're looking for trainers that can provide you double duty, not only with the Farm Robotics Challenge, but also with Skills USA, this would be a great place to start your Farm Robotics hardware. This is the Mech Lab, the training system. So we were in Taylor Farm's gigantic facility in Salinas the other evening for a tour, and all of the components that you see here, the pneumatic valves, the tubing, solenoids, this is all stuff that you see in big facilities like Taylor Farms. Festo is the global leader in automation and pneumatics hardware. And so there is a very, very gentle learning curve when you learn on the equipment that you're going to see out in industry. So this is the first of those three stations, touching on all of the objectives that you see there. Here's the second. It's got an optic sensor. It has an inductive sensor. We talk about separating metal out of, say, green leafy vegetables, which is, again, exactly what we saw in Taylor Farms the other day, using sensors to make sure that food is safe and clean. And then this third handling station here, getting into, again, grippers, solenoid valves, sensor technology, programming, logic. And then they have just recently added a collaborative robot station to work alongside the Mech Lab. It's got a Dobot Magician on there. Again, comes with hours and hours of curriculum, and also available on an online LMS, so it's very easy to access. And then stepping away from Festo, we also partner with a company called Matrix. This is their Formula All code, little race cars that students can code with a variety of different programming languages. So if you're more familiar with Raspberry Pi or Android devices or Linux, it is agnostic when it comes to that sort of stuff. So coding languages, whatever you choose, you can use with these. And that is about it for me. If you have any questions, I'll be in a breakout room, and please do look through that catalog that I shared at the beginning of my presentation. Thanks, everybody.
Excellent. Thank you very much, Greg. Okay, so next up we have Suma from Gather Technologies. Where'd Suma go?
I'm right here, Eric.
There you go.
All right, I'm gonna share my screen.
There you go.
All right, thanks, Eric. Thanks, Maria. Hey, everyone. Really honored to be here with all of these companies. So my name is Suma Reddy. I'm the co-founder and CEO of Gather. And as a teacher educator myself, really excited to introduce to you our robotics versatile, simple platform for schools. So first, who are we? We're a Merced, California-based company on a mission to build simplified AI-powered robotics tools for schools and farms. The Gather platform autonomously transports different types of crops and materials in field and around the school, farm, and school. So our goal is to empower students to build, develop, and innovate in ag and STEM. 4 key features: 1, a simple customizable design; 2, compact and portable compared to other kind of transport type systems; 3, cross-disciplinary curriculum; and 4, budget friendly. So we are built specifically for high schools. So our mission is really around making ag robotics simple, affordable, and accessible, not only for the teachers, right, and administrators, but also for the students. So you can come in 3 different ways with us. 1, whether you're computer science, ag mechanics, right, you probably have a different type of background as a teacher. So this curriculum for teachers provides the platform, the kit, teach the teachers sort of virtual session to walk through the educational modules, right? And you can even come in and build the Gather rover with us if you're kinetic and want a hands-on experience. Secondarily, of course, is the challenge. If you already have teams, right, selected, take the platform, the kits, and just kind of use the modules as a guide. And 3, we're building a community of educators. Like I said, I'm one myself. We really want this feedback to build a really good program. So 1 on the curriculum, we'll jump through this if this feels relevant to you. About 9 different modules focused on 1, building the system, and the second really on the development and software autonomy component. Building the system means building the hardware platform from scratch. So you see 3 students here working on this: the mechanical, the electrical, and then the power on and diagnostics. So on the mechanical side, right, everything from interpreting bombs to using rivet tools, QCs, right, and different kind of activities to make this really fun and engaging. That's one example. Happy to dive in during the breakout session. On the autonomy side, find that this can be really intimidating for some teachers. So we have really broken this down to be as simple as possible, right? Unless your students are already pretty advanced in computer science, right? And so, here's a module basically on vision and motion. A lot of words here that maybe some of you know, some of you don't, but don't get intimidated by it. We're here to walk you through it. And our goal, from our understanding, right, most of the schools are based right here in California. So we're really integrating into goals and standards, whether that's manufacturing and product dev, ag and natural resources, engineering and architecture. So we worked with one teacher, an ag mechanics teacher, who walked us through sort of pathway D and where we might fit in. You see ag machinery, power systems, right, electricity, wiring, personal and group safety practices, et cetera. So we'd love to understand this even better working with you. The second kind of place where you can slot in, right, of course, is the challenge itself. And so, what would a student do? Here's a snapshot of the system. A lot of words here, but basically, what can they customize? Number 1 is on the mechanical side, right? And that's using things like wheelbarrows, trailers, mower sprayers to move things on the field. And so they can customize that. The second, is the autonomy, right? Autonomy is really around getting the robot to move. Do you want to follow a road? Do you want to follow a person? Do you want to do point to point, etc.? So there's some information here on battery, towing capacity, 800 pounds, etc. Those are kind of the specs that would stay static for the student. So on this challenge, like Amiga, right, we'll offer the $1,000 Innovation Award. We are going to speak with the organizers to see if we can break this up into smaller awards, for example, 4 awards, $250 each, depending on the rules and regulations of the challenge, but kind of to spread the wealth and spread the feeling of joy. So in terms of the challenge, as we know, you guys know all of this around defining the problem, objectives, testing features, but we want to give you two real case studies. So here, Ray might want to transport crops efficiently, and so he's looking for a solution. So first question, what kind of attachment? He says trailer. So great. Objective, haul up to 225 pounds. So the student must meet that objective. Autonomy, they want to follow a person. So maintain that safe driving distance. Ray also might say, I want a remote control, right? So you enable that. And then of course, there's some safety features that are always built into to whatever you're going to do. Here's an example of what that could look like, right? Where you see this Gather rover, that small little system dragging a huge trailer around the farm. Second quick example is for vineyards. As you might know, 99% of table grapes are grown in California, which is pretty amazing. And wheelbarrows are used primarily to haul crops. So it's very time consuming, very labor intensive. So attachment here, not a trailer, but a wheelbarrow. So how do you actually build that into the system? The autonomy, row following, right? So following the vines, being able to sense them and go down a row. And you might throw in some efficiency goals and safety goals, right? That's up to you as educators and as well as for students. So what that could look like here, bumping, going down the road, dragging some grapes right there. We also wanted to say, as a non-ag challenge, right? There's a lot of ways you can play with this beyond the competition. We were speaking to some folks here who talked about, that shouldn't say robotic transport, but like a use for a maintenance worker at a school, right? So they might want to put a utility cart, a bin hauler on the system, follow them around the thing, do campus route navigation, maybe from a maintenance shed to a gym to a cafeteria. And then have safety elements as well. So no one has built this, so it's kind of an invitation to you if you engage. So just last thing, sort of on pricing, we do think we're the lowest cost on the market for this kind of system, base 12,000, but specifically for this group, we're offering $11,000 for the robot, API, the modules, and the indefinite support. Lastly, just a call here, as our mission is really around building the future of work in ag, meaning training future ag technologists, improving our food resiliency, right, making farm work safer and easier. And what's been really exciting is enabling and energizing students. It's been fantastic to see students connecting with their families who work in the fields, themselves, with their aunts and uncles, their local communities, and really understanding their connection to the food system better. So there's my information. I'll also put it in the chat. Like Amiga, we are a sponsor as well. So I'll put that page as well. So thank you all for your time.
You're muted, Eric.
Thank you, Suma, for your presentation. It was very good. Thank you for the time. How about Andy? Let's see what Parallax has, and we'll go from there.
Okay, can you hear me all right?
Yes, sir.
All righty, let me go ahead and I'm just real quick copying the link and about to share it into the resources. That's not working out. Okay, I'm going to put it in the chat. Okay, here it is. Okay, so that is for all of you to make a copy. I wanted to make sure you had a link to this slideshow because it is a treasure trove of other links. So here we go. All right, so what I'd like to talk with you about today is the Parallax Cyberbot robot. This is a small robot that can be equipped in a classroom with a 1 to 2 student per robot ratio. And that is favorable for some introductory lessons before moving on to, say, a larger robot. This, if you want to take a screen capture of it, is a link, 3 ways to get to this slideshow. Again, I'd like you to save this slideshow because of the fact that it has so many useful links in it. All of our curriculum, or at least our student-facing curriculum, and much of our teacher-facing only assessment materials are kept for teachers only, and then everything else is published on the web. Anyway, here is the Cyberbot. It has a microbit brain. This is a processor that has built-in display, push buttons. It has an edge here where you can connect circuits, as well as a built-in accelerometer, compass, and radio for networking. So just on its own, the microbit is great. These are links to a whole bunch of fun little activities with the microbit only as warm-ups at microbit.org/projects/make-it-code-it. Also, I have links here to some parallax lessons in both MakeCode, that's a block programming language, and Python, with sensors instead of a pre-calibrated scientific sensor. These are sensors that that students get to wire themselves and then work on potentially calibrating, as opposed to, well, it's more about learning how to read the sensor at an electronics level, as opposed to a prepackaged sensor. The robot itself is great for introducing fundamentals. Like, here is a Python script that has statements in this area right here to make the robot move forward and turn right. Well, you can indent those statements and then add one more statement above it to add an important feature of programming, which is repeating something a certain amount of times. And so students learn lessons, first of all, on the screen, and then secondly, through the robot, so that they can apprehend a valuable language such as Python, which is used, as you've heard, in some of the other robots during the other vendor presentations. With the Cyberbot robot comes a number of sensors. With the small time limit, I'm going to skip playing these videos, but this is an example of a lesson where a contact sensor is built on the robot's prototyping area, and then it navigates and bumps into things and turns and finds new directions. We also have, in the stock kit, light sensors that students can build and program the robot to follow or avoid light, find a garage to park in, that kind of stuff. Also non-contact infrared flashlight sensors, where the infrared is shined out, and if it comes back and reaches the sensor, the script can know to turn away or toward an object that it detects. This is a fun one. I'll go ahead and show it to you. It has to do with the built-in radios in the microbit. It makes it possible for networked applications. Like here in this example, there's one microbit connected to the teacher computer, and all the student robots are essentially receiving the same command over their radios. So that's pretty neat. And F5. There we are. Tilt control with another radio connected microbit. And then we also have a machine learning and vision integration package, which you might find to be attractive as a primer for some of the larger robots. So basically attaching this, it's called the Husky Lens machine vision module, onto the robot, and then connecting and then wiring it up so that it can communicate with the robot. This will allow you to, sorry about this, let's go back. The vision module can then be configured to recognize certain things. Like here, it's recognizing a potted plant. We've got certain colors and other objects that the robot can recognize, and it can also report the coordinates. So this is a good primer for using some of the vision systems on the larger robots. And here it's detecting colors in a field of colors. And it can also do a road following example using its line detection feature. So these are important getting ready lessons, and then detecting certain objects. And there's also an option of a tilt. So we have pan through the robot's ability to rotate in place, and then this little servo here is connected to it so that you can have both pan and tilt with the camera module. The servo, the camera can also be mounted just as is, and then the servo can be used as an actuator. At any rate, so this to me is a starting point before going to, and here's a nod to Amiga's awesome, amazing robot, as a starting point in the classroom with a one-on-one or two-on-one student to robot ratio before going out into the field to work with the larger robots. Yet we get the valuable lessons in Python and et cetera, as again, preparation for the larger robots. This is make code. So this is block programming, and each tile here is a chapter in a student workbook that the students can go through. This is the Python version. It's all the same lessons, but basically with the Python programming language, which is really the best language, I think, for students to get started in robotics if they don't need the block programming starting point. And then since the lessons are essentially the same, if they start with block programming, they can also then step into Python programming after that. Again, this is all free. It's all on the web. It's all student-facing lessons that you can, simply follow the link and go to the page and actually open, navigation by light, and then go through the entire chapter.
Well, thank you, Andy, for sharing all this with us.
You are welcome. I have one last thing to say, and that is that there are slides for workshops, for purchasing if you need it, and then a little summary slide, but I guess I'm over time. So, and then how to get a hold of us. And thanks for watching.
And you get to share more of this in a few minutes, Andy.
Okay.
Good deal. Moving forward, so Andy presents something that's probably real, and while it might be small, is very valuable to our Farm Robotics Academy scenario. And then let's see what Matt has from Klein Education.
Awesome. Eric, can everybody see screen there?
Hang on, double
Does that
click.
look like it's sharing?
It's still black on my end. There it is.
Perfect. Well, cool. Thanks for the introduction, Eric. Yeah, my name is Matt. I work for Client Education System. So,
Hey,
company,
Matt,
we specialize in training. Yeah.
Matt, I'm gonna. You got a bad connection. I have to turn off your camera.
Oh, shoot. Okay, let me do that. Is that better?
Yes.
Okay. All right. Well, anyway, I specialize in training in the industrial trade. So we work with hundreds of schools up and down the West Coast. I myself, I'm based out of Northern California. But like I said, we work with hundreds of schools. We work with every community college in the Central Valley. Some of the largest employers in the country. I actually just came from a meeting at the Wonderful Company here in Bakersfield, where we're training their students to be maintenance mechanics, but represent a wide variety of different areas and work in so many different CTE pathways. But But some of the companies that I wanted to share with you guys today were a few companies specifically around robotics and how that I thought could have some applications in the Farm Robotics Challenge, and maybe some real world problem with our solution. So first one being Fanuc Robotics. Fanuc Robotics has about over 65% market share in the industrial robotic arm space. And so we actually are their exclusive educational distributor on the West Coast. So we have multiple educational packages of Fanuc Robotics that will come on what we call our education cert carts. We've got a full curriculum that's about 90 hours long, mapped around learning how to program these robots. They're still fully industrial robots that you would see in a normal industrial setting, or even in a perhaps agricultural setting. So, and students would go through, actually the instructor would go through a certification training, and then later on be able to offer their students Fanuc certifications. So, multiple add-on you can add to a Fanuc cert with some examples like a conveyor. You can add vision systems, PLC, different end-of-arm toolings. One example of a Fanuc robot in an agricultural setting. This is actually, you can see the Fanuc robot on the back of a harvester that's picking rolls. So that's the robotic controller at the front of the harvester there. And then we've got our big yellow Fanuc robot on the harvester around and up to rolls to be distributed. So the next company share was called Mind's Eye Robotics. Mind's Eye specializes in very actually agricultural applications of robotics, just in a scaled down version. So they've got autonomous mobile robots like autonomous tractors. We've got autonomous drones. Again, each product that we offer with Mind's Eye has a full 45-hour curriculum course written around it, and it's gonna go into things like GPS, programming, sensors, so on and so forth. So a couple of the products that I thought would be most applicable to the Farm Robotics Challenge are our UAV drones lab, where students are actually going to construct these drones. They're going to go through a curriculum, learn about programming, the remote controls. There's actually a flight simulator and a gimbal that comes along with it, so they can get comfortable flying these drones indoors prior to taking them outside. And they're going to learn about the GPS and compass and the telemetry and all that stuff. So again, 45-hour course. Each lab is designed for about 3 to 5 students. And it's a great introduction to that drone technology. The next one being our self-driving autonomous tractor. So this is basically a scaled down version of what you might see in a real field setting, like you can see in that upper right hand corner of that picture there. So we've actually gotten it down all the way to a 2-centimeter precision. So it's extremely accurate. It's going to be programmed to be fully autonomous after these students go through the 45-hour course. It's got multiple different attachments you can add onto the back of it, like a sprayer or a weed or anything like that, that are all fully functional. So for example, with the sprayer, you could actually fill it up with water or fertilizer and program it to go around your school's small field or parking lot to run a sample route. And the last one is called Stokes Robotics. A lot of you have probably seen the robotic dog on whether it be social media or at a conference or anything like that. You might have seen a robotic dog running around. So Stokes Robotics, they take these robotic dogs, and we write an entire curriculum course around them that introduces students to robotic programming and operations. Similar to what many of you have said today, we can program these robots in Python, C++, Scratch, etc. So you can see that on the left, we've got a robot dog in a field. What's cool about these is there are many different add-ons you can make to these dogs. You could put a robot arm on top. You could put they're used in law enforcement or military situations very often, but for the agricultural side of things, it'd be pretty neat to put a robot arm on there and it could go around and harvest crops or whatever it may be. You can see it has object detection on the front of it, LiDAR technology. So once it's programmed to be autonomous, it's not going to go running into things. It'll see an object in front of it and work away around it, work a clear path around it. So that's our robot dog on the left. And then on the right side, we've got one of our newest robots, which is our humanoid robot. So I wanted to share that with you guys. I'm sure that the students would be able to get creative on how to apply this humanoid robot. I'm not super familiar with it yet, but it could be a cool way to solve a real world problem with it. So again, both of these units, like I said, have a full curriculum course written around them to introduce the students to the technology that's involved in them. And then they would be able to program it to do, independent tasks. So
Wow.
that's it. I can throw my contact info in the chat, but I'll be in the breakout room. Thanks,
Thank you
Eric.
very much.